we're going to be working on some rather beastly limiting reactant problems. That's enough. What we're going to do here is we're going to try and work out two examples of a real tough limiting reactant problem, harder than even the regular ones, which are bad enough. So let's look at this reaction right here. We are going to take gold nitrate and do a single replacement reaction. The iron is going to go in and replace gold and gold nitrate, making iron nitrate and regular gold metal. Let's just say we mix together, well, I don't know, 7.77 grams of gold nitrate and 1.65 grams of iron. And our question that we're interested in is how much gold are we going to get out of that reaction? And so what we have to do here is figure out if one of these guys is going to run out, is going to limit how far this reaction can proceed. So we have to first, just like every other limiting reactant problem, convert these into moles. So using the molar mass of gold nitrate, we will change that into moles of gold nitrate. And find that we have 0.0203 moles of gold nitrate. Doing the same thing with the iron, the other reactant, changing it into moles using its molar mass, we have 0.0295 moles of iron. Now, if you're really good at math, if you see numbers well, some people will recognize right away that even though that there is less of the gold nitrate than there is of the iron, that the iron is going to run out first. And it's because this isn't a one-to-one reaction. The balanced chemical reaction, which is the most important part of well, just about everything, but especially for finding limiting reactant problems, tells us that there's a 2-to-3 ratio between the gold nitrate and the iron. And if you're real good at math, you'll know by looking at this that this is not a 2-to-3 ratio, that we are definitely missing some iron here, and that we're going to run out of iron first. Okay? Now, if you don't see it, don't worry about that. That's I have a way I'm going to show you how to fix that. But if you can see it, then you already know that the gold nitrate is going to run out before the iron does. Okay? But let's say you can't. Let's say you don't see that, or it's too complicated of a ratio and you can't easily tell. The next step that I like to do is take the moles of the gold nitrate that I have and divide it by its coefficient. So to run this reaction once, I need 2 moles of gold nitrate, or actually to run it 1 mole of times, I need 2 moles of gold nitrate. That means we can run it 0.0102 moles worth before we run out. And if we do the same thing with the iron, take our moles of iron that we have and divide by the coefficient, we'll figure out how many times we can run it before we run out of iron. And you can see this way then, you're just comparing numbers, and whichever one is smaller is going to run out first. Since we can only run this 0.00983 times before we're going to run out of the iron, and then we can run it 0.0102 moles of times before we run out of the gold nitrate. Iron is our limiting reactant here, and once you got that finished off, once you know that, it's just another regular stoichiometry problem. It's just another limiting reactant problem. But doing that is the hard part of these difficult stoichiometry problems here. So once I know that iron is my limiting reactant, I always start with the limiting reactant to do my calculation. I could go all the way back here. I'm starting off with moles of iron. I could go all the way back and start with a mass of iron that I gave on the other side. I forget what it was, like 1.65 grams, I think. I could do that, but since I already figured out how many moles I had, I already have done this calculation, I might as well start here. So I'm in moles of iron, and when I want to go into moles of gold, I know that I have got a 3-to-2 mole ratio. For every 3 moles of iron, I have 2 moles of gold. And then I'm going to, so that gets me across the mole ratio bridge. Now we are into moles of gold. And now I want to go into a mass of gold, so I need to use the molar mass of gold. For every 1 mole of gold, I get 196 grams. And so when we mix those two reactants together, we can expect to make, 3.87 grams of gold. And because this isn't a 1-to-1 reactant ratio, that's what makes this a little bit more difficult. Once you figure out which is the limiting reactant, all limiting reactant problems are the same. But figuring out the limiting reactant in these problems can be a little difficult. Okay, let's take the reaction that's going on inside you right now. You're taking glucose and oxygen and making carbon dioxide and water, and that's releasing some energy as well. So the balanced chemical reaction here is 1 glucose and 6 oxygen gives me 6 carbon dioxide, 6 water, and some energy, which we won't worry about it for the time being. Okay. Let's say that there are 786 grams of glucose and 2,345 grams of oxygen, and the question asks how much carbon dioxide will be made. If that's the question, we have to look at these reactants and figure out which one is going to run out first. And so we have to convert them to moles. Always start the same for these. Take your reactants and change them into moles. So for our glucose, the molar mass is 180.61, and we're looking at 4.36 moles of glucose. Now the oxygen, if I change the mass of oxygen into moles of oxygen, I'm going to have 73.28 moles of oxygen. Now, you have to look at these and compare them to the ratios that you have up here. Our ratio is 1 to 6. So I need 6 times more oxygen than I do glucose. And so if you're good at math, again, you can look at this right here and say that is easily 6 times as big as that. That in fact we're going to definitely run out of this first because we have plenty of oxygen. But if you don't like that, and if you want to calculate it just to be sure, to make sure you're not making a mistake, you can always take each number of moles and divide it by the coefficient. So I can go back and grab my moles of glucose and divide it by 1, because it takes 1 mole of glucose to do every reaction. And so when I do that, I can run this reaction 4.36 times. If I do it with my oxygen, 73.28 moles of oxygen, I'm going to divide this by 6. The 6 coming from all the way up there in the 6 right here is, oh boy, smartboard errors. That 6 right there is the same 6 as right there. I can run this 12.21 times before I run out of oxygen. So I'm definitely going to run out of glucose first. That is my limiting reactant. So now that I know my limiting reactant, I'm going to take it and I'm going to calculate how many moles of carbon dioxide I can make. I have a 1 to 6 mole ratio. For every 1 mole of glucose, I can make 6 moles of carbon dioxide. So 1 mole of glucose makes 6 moles of carbon dioxide. And then I can go from moles of carbon dioxide, get across the bridge there. I'll go from moles of carbon dioxide into mass using its molar mass. Carbon dioxide is 44.01 grams per mole. So this will make 1,150 grams of CO2. Right, and then the next thing they're going to do to you is they're going to ask you how much excess reactant remains in this bad boy. And so this is the last step in an already hard problem. So again, go back to your limiting reactant. Always go back to the thing that you've determined to be limiting, and then just work out the stoichiometry with this one. So we know that we're going to run out of glucose, and we know that oxygen is going to be the reactant left over. So we'll calculate how much oxygen we're going to use up. I know that for every 1 mole of glucose, I use 6 moles of oxygen from the mole ratio up above there. And I know that the molar mass of oxygen is 32 grams per mole, so we're going to use up 837 grams of oxygen. If I started off with 2,345 and I used up 837 grams, that means that I'm going to have 1,508 grams of oxygen left over.